the one-dimensional one that's due on Friday. And I looked at the quiz results. Don't anybody panic, because I do drop a quiz. So I did look at quiz results, and I will go over the problems that cause most people the most issues. So, but I do want to start with a couple of things before we get too far into that. So, document camera, do you guys see the document camera over in Enid? Yay, good.
We do.
All right. So, where we left off last Wednesday, before you guys got a quiz last Friday, is we had written down that if I had a change in x that was going to equal the velocity times the time. We had gotten to the point that we had at least written down our equations, our kinematic equations, that we were going to end up using so that you guys could get homework done and other things done, including the quiz done. And so these are the equations that we had gotten to. And we had talked about how velocity was the change in x with respect to time, that velocity was a vector quantity, and this could be written as a derivative. And we had gotten that acceleration was a change in velocity with respect to time, and that could also be written as a derivative. But what we didn't write was it could be written as a second derivative, like that, in terms of calculus. So if I'm writing in my calculus, I can see these kinds of things, and I would get to that point. We had talked about, I'm going to give people a second because I see writing. So that becomes kind of our toolbox, if you were. Just a couple more. So that's our toolbox, and we had talked about that if one-dimensional motion could be anywhere along that kind of a line, one-dimensional motion could be anywhere along this kind of a line, and we talked about how I could ultimately change it to have along that kind of a line. The key was I was only going back and forth along that line. Okay, so that was the key. We also had talked about that speed was not necessarily equal to velocity. And we went through a couple of different examples, or at least talked through a couple of different examples before we lost Enid on Wednesday. Well, when I looked at the quiz results, I discovered that the two problems that most people had issue with, if they had an issue, were related to this idea of speed and velocity and looking at things in one dimension. So we're going to work those problems so that we can actually see them. So one was, it said that, depending on which version you got, it said that a student drove from one point to another, so we're driving from one point to some other point down the road. The odometer on the car read that it was 16 kilometers. We had no idea what the route was. Don't have a clue as to what the route was. And the time that it took to do this was 17 minutes. And actually it was given it to you in 3 significant figures. It was 17 minutes. And we're asked to find the average speed. Well, the average speed is going to be my total distance divided by the time. And the key here is to make sure when you're working in WebAssign what the distance was in. This was in kilometers per hour. So my guess is if you missed it, the initial time, what you did was you put in 16 kilometers and you divided by the 17 minutes and you got some value in kilometers per minute. And that would have been a big because I want, or WebAssign asked for it, or I wanted it in kilometers per hour. So the first thing we have to do is convert my 17 minutes into an hour. So there's 1 hour is 60 minutes. And if you put that into the calculator, you get, that's not right. Helps if you type it into the calculator correctly. It gives you 0.283 hours. So now I take my 16 kilometers and divide it by my 0.283 hours, and I get a value of 56.5 kilometers per hour. That would be my average speed. In the second part, we find out that I drew this out on a map, that here is destination B, here is destination A, and we find out that the destination actually along what we call as the crow flies, obviously her route following streets was more like something like that, but as the crow flies, we find out that that distance is 10.3 kilometers, and we want to know the average velocity. And we're also given this angle, but I really don't need that angle because this is motion in one dimension. I just need the magnitude of that vector. The angle was put in there just to throw you off. So now my average velocity is my 10.3 kilometers. We've already converted into hours, so that's 0.283 hours. And I plug that into the calculator. And this gives me 36.4 kilometers per hour. So speed and velocity in this case are very, very different. Very different. So if I'm looking at, and part C was, all right, if she returned home by the same path, okay, so let's say this was the path that she got there. Okay, and this is where reading the question becomes very important. If she returned by the same path, that means I went backwards. We want to find the average velocity and the average speed. Well, the average velocity, remember my average velocity relates to the velocity final minus velocity initial. If I've returned to the same place, my average velocity is going to be a big fat 0 because my change in position is 0. So it doesn't matter how long it took. If I went from one spot to that spot and back, and I'm exactly where I started, my average velocity is 0. My average speed, however, is a little different, and this is where the problem is here. I went this way, that's 16 kilometers, came back, that's 16 kilometers. So the total distance traveled was 32 kilometers, and I went in 7.5 hours. And if I do that, I get 4.27 kilometers per hour. So the likely places for error are, you don't want that minutes, you wanted it in hours. This one is you ended up putting a number in when you didn't have to. This one may be that you forgot to double the distance. So those were the key places where that particular problem may have caused you a bit of consternation. questions? Start a sign-up sheet. Thank you. All right. The next one that seemed to cause people problems was the football player or the quarterback. So this is where drawing your picture really, really helps. All right. So our football player.
Scrawny.
Huh?
Scrawny football player.
Scrawny, yeah. Our football player. And did a really nice run, went 15 meters, and happened to do it in 2.9 seconds. Meets another football player, immediately gets bumped backwards 3 meters. And we know that time was 1.78 seconds. And then from there, breaks free, happens to run another 26 meters in 5.2 seconds. So the first part of it was to find the velocity during each segment. So if I call this segment 1, segment 2, segment 3, well, that's easy enough, okay? But I have to keep an idea about the direction, right? I have to keep an idea about the direction. So segment 1 is going to be my change in distance with respect to time. And that's going to be 15 meters divided by my 2.9 seconds. And if I plug that into the calculator, gives me 5.17 meters per second. The second one, still doing change in position with respect to time, except now my final is 3 meters behind where I started, so I end up with a negative because that's going to give me my direction, 1.78 seconds. And that gives me 1.68 seconds in the negative direction. And the third segment, my change in position with respect to time, is going to give me 26.0 divided by 5.2. And this is in meters per second. That gives me 5 meters per second. So guess is this negative caused consternation? Because it's going back in the other direction. Because remember, vectors have direction and magnitude. So the vectors are going to have direction and magnitude. Now the next part was calculate the average velocity for the entire motion. And this is where drawing our picture really, really helps. Because if this is my starting point, and we say that that's x equal to 0, this is my finish point. I got to know where that is. So I have to do the follow back here. This ends up being 15 meters. This ends up, I'm going to add from here to here 22 meters. So the total, you're right, 23. The whole total there is 38 meters. Now I have to have my total time. So my total time is going to be 2.9 seconds plus 1.78 seconds plus 5.2 seconds. If I do that, gives me 9.88 seconds. So my velocity, change in position over the change in time, and I got to move this up. Change in position over the change in time is going to be 38 meters divided by 9.88 seconds something like 3.85 meters per second. So the likely errors in this one is the big one is related to what was my change in position. That was the big error. Okay? Questions? All right. So let's talk about one of my favorite problems. You have something that's sort of in the example book, or the examples in your book as well. But it's a problem I always like to use. And we're still in one-dimensional motion. And we'll talk about it and we'll work through lots of different pieces of it. Because a lot of this is looking at exactly what question you asked. Almost. Almost. So I've got my little person up here at the top. And we're going to toss a ball. And we're going to measure the ball from the edge of the building. And we're going to toss the ball up with an initial velocity of 2 meters per second. Now, it's going to go up. And we're going to just miss it catching, and it actually is going to fall all the way down here. We can approximate this as one-dimensional motion. I've actually drawn it as a little bit of two-dimensional motion. But basically, if I have my hand out over the edge and I toss the ball up and come back down, and as long as there's not a whole lot of wind, it's going to fall right back straight down in its path. So I'm drawing the picture just a little distorted to be able to see that. Now, what we're going to do, because we can, and gives us ourselves a little bit of a time, because hopefully in my lab you learned a bar trick. Right? When I taught the lab, you learned a bar trick. The bar trick is the person who drops the picket fence better be the person who catches the picket fence, otherwise my picket fence is going to break.
Dr. Grimm didn't tell us to catch it.
Did you fall to the floor?
He told us just put something under it.
Oh yeah, so you actually let it fall all the way to the floor.
No,
I
not the floor, but just like to our lab stage. Right?
Okay, well that was another way of doing it. So, but I have people catch it because I don't want my picket fences hitting the floor because they have a tendency to break. But the person who catches it, person who drops it, has to be the person who catches it. And we did the dollar bill trick where you demonstrate that the dollar bill falls and you catch it. Okay, that's one of your first pieces because it's reaction time. Humans don't have the bestest reaction time. Okay, so we're going to time it. We're going to start the timer, and we're going to know that the time that it takes to fall, we're going to give ourselves that time that it takes to fall is 3.6 seconds. All right? We know we've got the initial velocity goes up. So the problem may only give us this amount of information. But there's other information that we know. There's other information that we know because this is one-dimensional motion. We probably know, in fact, I do know that we know the velocity at the top.
Zero.
It's 0. The velocity at the top is 0 meters per second because at the very top we're making an instantaneous change from the positive direction to the negative direction. So we got to go through 0. So we know the velocity at the top. Okay? What else do we know that we're probably not explicitly told in the problem?
Gravity.
Yeah, we know the acceleration due to gravity. And we use 9.8 meters per second squared. And we are going to put gravity in that direction. So those are things we know.
We can't see all of it.
You can't see all of it? Is that better?
Yes.
Okay. So those are things we already know. The other things we know are, we know that V final is equal to V initial plus AT. We know V final squared is equal to V initial squared plus 1/2 AT squared. And we know that the change in position, which we're going to go change in height, is going to equal V initial times time plus, I didn't write this right, sorry. Guys, this was 2 times acceleration times the height. And this is 1/2 AT squared. I have my 3 kinematic equations that I can play with. So we know a couple things. So this one's easy, all right? Because we know V final, we know V initial, we know G. So I can rewrite this one. So I can get V final is equal to V initial minus gravity times time. I know everything but time, so let's get that part. So I get V final minus V initial divided by negative gravity is going to give me time. I can find the time that it takes to get from here to here. I can actually find that time. So let's do that. My final, V final is 0 meters per second. My initial was 2 meters per second. I'm doing it at negative 9.8 meters per second squared. And I end up with 2 divided by 9.8 gives me 0.204 seconds. Now let's look at I got meters per second divided by meters per second squared. Meters are going to cancel. One of these seconds cancels, and this is 1 over seconds divided by 1 over seconds squared, but this one goes away, so there. So I end up with seconds, so I'm good. By symmetry, we now know this time. We know that time has got to be 0.204 seconds. So a question I might ask is the total time the ball is in the air. I get 0.204 to go to the top, 0.204 before where I start timing the timer, and I get 3.6 from here to the ground. So I can get that total time. Gives me 4.008 seconds. I can ask, what's the velocity down here?
0.
This one? Just before it hits.
Oh, just before it hits.
Just before it hits. What's the velocity?
9.8 times 4.008.
I would do it this way. Okay. Velocity final is equal to velocity initial minus gravity times time. I have to account for the fact that it had an initial velocity going up. So my final velocity is going to be my 2 meters per second minus gravity, which is 9.8 meters per second squared. And now I get my time in here. If I plug that into now this gives me these cancel, so I can add these two things together. Gives me a negative 37.3 meters per second. I can also find this, I can find either this total height or I can find this height. And this is where it becomes key as to which question is asked. Because what if I'm asking you the height of the building? Now, one of the things we know at this point by symmetry that we're now going a negative 2 meters per second. Or I could calculate that by using my velocity final minus my velocity initial. But at that point, I'm going a negative 2 meters per second. So now I can do my change in height of the building is going to be my negative 2 meters per second. Now I'm going to do the time that I'm falling, 3.6 seconds, minus 1/2 9.81 meters per second squared times time squared 3.6 seconds squared. Second squareds are going to cancel. Seconds are going to cancel. I can actually add these together. So this gives me a negative 7.2 meters minus and if I plug things into the calculator right, I get a negative 63.5 meters. So I actually am going to go down a negative 70.7 meters. And if I don't study any one particular example in one-dimensional motion, this would be the one example I want to know backwards, forwards, upside down. Because we will see that over and over again. And we'll use it. So you really want to look at, because this has every aspect of our one-dimensional motion problem. And we talked about the questions that we got. So I'm going to look at the types of questions that you might be asked on that picture. So I got my building. Here's the ground. And depending upon what piece of information that you have, here's my motion. It's one-dimensional. Okay? We're just exaggerating it so we have a place to write it. I've got a reference point here. You may be asked for this height. You may be asked for this time. And a lot of this depends on what information that you've been given. You may be asked for this time. You may be asked for this height. You may be given this height and asked for this velocity. You may be asked for the velocity at any given point on the downward piece. You could be asked any of those velocities. You could be asked any time along these pieces. So there's lots of different questions that you could be asked. And depending upon how the question's asked, I may have to add some of these together. And one of the questions might be, what was the total height fallen? Which would be our h prime plus, that's right, our h prime plus our h. From the top of the part to the bottom of the part. So we can use this problem to ask a whole bunch of questions. Because I think one of the old questions is I have a person out here looking out a window, you know, my person's looking out a window, and they want to know what the velocity is as the ball passes the window. So we can ask lots of different questions related to it. Lots of different questions related to it. So where am I at? Okay, so I want to look at a real world problem and look at what happens from using a video and motion video. So in Blackboard, so hopefully over Nina, did you guys see in my Blackboard? Yeah, good. So in the box called Smiley Items, here's the video, okay? So I've done a video analysis, and I've used a little popper, and I've actually collected the video and used the video tracker software that you guys have access to, and captured the little popper pop up and pop back down. I have a reference in there so I can actually measure reference, and the tracker software gives me a data file. So we get a nice little data file that track the center of mass, and it actually falls up and down. I've got the data file in there so that you can actually see the data file. I want to go. So you can actually see it again. It pops up and pops down. I actually get a little bit of a flip. So this is real live, you know, a real live example. I happen to stage it in my office, so it's there. But now, where's my smiley stuff? So here's all the smiley stuff. I've got a set of PowerPoints, and I think you guys have access to them, so you can actually see the data and all of this good stuff. So from the current slide. So basically, my software gave me my position versus time, and it did a curve fit. And I did a parabolic curve fit. So that my sources of error for this would be, did I really get the center of mass of my little smiley when I did the video plucking of the data to pluck it out? Since it's not perfect, I didn't get it exactly right, but I got it pretty well because this is a parabolic fit to the curve. Here's the actual data. So this is time, 0.1 second, 0.13 seconds, 0.17 seconds. So here's my time. This is in millimeters because I could actually, with that tracker software, I could set it to scale. So this is actually set to scale. So I've got that. I've calculated, and when you calculate in Excel, I've got a position and time. I've got a position and time. I can calculate a velocity because I can take the difference between these 2 points and take the difference between that time and calculate a velocity. So that's my velocity in millimeters per second. And I can do that for the entire part. And then when I flip over the top, I'm now going in the negative direction. So I have a velocity versus time plot. I can do a velocity versus time plot, and I can do a position versus time plot. So here's my position versus time plot in Excel, and I did a curve fit. And it gives me y is equal to some value to just my parabola in front of the in front of the x squared, some value in front of my x, and then some initial starting point. And I get my regression to say how good of a fit is it. If it's 1, it's a perfect fit. If it's close to 1, it's a pretty good fit. Remember your math and actually matching graphs and looking at your lines, that's a pretty darn good fit. So I have that, but we know that this actually physically means something. So here's my change in position, except now I'm putting the initial position over here. So per this particular diagram, my initial position was 192 millimeters below what I set as my 0 in the y direction. I have an initial velocity and it was traveling upwards at 2,773 millimeters per second. And I have it's a negative 4,217 millimeters per second squared. But we know what this looks and matches up with. If I make x time, because time is that axis, and I make position y, I can rewrite that as y is equal to one of my kinematic equations, and now I can read gravity right off of the equation, because this value right here, minus 4217, has got to equal the acceleration divided by 2. Multiply that times 2. 4217 times 2 is going to give me 8420 something. I don't have the best gravity, but I've got a value that I could read right off the chart. I can do the same thing with velocity and put it as a velocity versus time graph. And we know that my velocity final is equal to my velocity initial plus the acceleration times time. So I can do the same analysis, and I've got a better best fit line. And for this one, picking the data off of my one-dimensional motion graph, it says that my gravity is a negative 9.197 meters per second. I've made the adjustment because I'm in millimeters and I get to divide by 1,000. But I can use my actual data in order to find out things like what's my acceleration, what's my initial velocity. You can find out those pieces. So types of word problems, people would always ask me, well, what type of word problems might I see? Well, these would be the types of word problems that you might see related to that kind of information. So those of you who are pulling your lab reports together, this is exactly what you guys did for free fall. You had a velocity versus time plot that you could read gravity off of, and some of you have your parabolic fit. Now you don't have the part that goes up because you dropped it going down, but you don't have the part that goes up. So now you can read gravity right off of your data. Now what you guys are doing in lab starting tomorrow is we're going to still do it in one dimension, except now we're going down an inclined plane. So we're going to have to adjust for the angle and look at the angle in there. We're going to have to look at that angle and make sure that we've got that covered. So let's look at that just a little bit. Since I have just a couple more minutes before we're going to lose everybody. So, if I have an object on an inclined plane, there's my inclined plane. I've got an angle. We're going to write a normal vector to my plane. Okay? This is at a right angle. Okay, that's at a right angle. So we have that normal vector to our plane, and what we're doing right now is we're just playing geometry. Okay? We're just playing geometry. And I have gravity. We know my acceleration due to gravity. I can draw it on there. It's going to go something like that. Okay? And gravity is going to go something like that. Now, if I've got my thing on an inclined plane, we know what it's going to do. It's going to go down in this direction. We know that's where it's going to go. But the question is, and we talk about these things all the time, is if I have something that looks like this, and I want to know the component that's along here, All right, I want to know that component that's falling along that direction. I got a few things I got to do, right? We know we got a few things that we have to take into account. So a lot of times what it's going to be really handy is if I have my gravity come down here, I'm going to draw my triangle just a little bit different. And I think I showed you guys early on that this angle on my inclined plane is the same as that angle. And I can use geometry to get me there. And you can go to Appendix A and you can kind of look at your geometry and you can kind of look at that. But we actually went back, I think we did it like on the second day. I put up a bunch of angle things that we could talk about so that you guys were comfortable looking at pieces. But this angle and this angle by good old geometry is the same. So I can look at G perpendicular and I can look at G parallel to my plane. And if this is G, I can look at that. What's nice about this means that this is the opposite side. That's going to be G times the sine of the angle. And this is going to be G times the cosine of the angle. And when we get to other motion and other forces on an inclined plane, this is going to be a nice way to think about what's happening along my plane. What's happening parallel to the surface of the plane and what's happening perpendicular to the plane. And then we will use, for reference, something called a normal. And that normal is perpendicular to my plane. So I've got some nice geometry that's going to help me out. So when you guys are tackling your lab coming up, that's really what we're looking at is that piece associated with that. Okay, that gets us through chapter 2. We're going to start chapter 3 on Wednesday. And that's vectors, if I remember correctly. And I'll see most of you tomorrow morning, unless there's questions. You guys good over there in Enid? All right.